go. All right. So, for example, you can actually do a very quick shortcut whenever you're working in organic chemistry. Lots of carbons and oxygens and nitrogens. And so what you can do is you can go, carbon is 4 steps away from noble gas. And so carbon typically wants 4 bonds. Okay? And so this would be carbon with 4 individual single bonds. This would be with a double bond. You'll recognize that one from the one we did second, right? See, that's the first one. That's the second one we did. And the other option would be where you have sets of 4 bonds, where you have a 3 bond on one, which is a triple bond, and then a single bond on the other side. Okay? Notice these right here are the geometries we had just talked about. And so, for example, the second one we did was trigonal planar, wasn't it? Okay. The first one we did was actually tetrahedral, and that's that camera stand looking one. Right? Okay, so let's talk a bit about non-bonding electrons and what they have in terms of effect on the shape. Now, there's 2 things you have to remember when we're talking about this. There is the electronic shape, okay, the shape of the electrons, right? And that is the electron geometry, or electronic geometry. There is then the molecular geometry. That's the shape of the molecule. So that'll be the atoms. We just ignore things like lone pairs in that case. Okay? They still affect the shape it'll take on, but we don't include them in what the shape is. Right? Okay. It's kind of like the chair. The chair excludes the space you sit in, right? That affects the shape, but that's not the shape of the chair, right? Because that's where you are. Non-bonding pairs of electrons are going to take up space, but they're going to be invisible in that molecular shape. Non-bonding pairs of electrons force bonds pairs closer together because they're going to be very large. They're going to take up a lot of space. Bonded electrons are going to be confined between 2 atoms, and that's what makes bonding pairs and non-bonding pairs a little different. When you're talking about a bonding pair, it has another nucleus on the other side of it, and so it's very tightly contained. The sort of easy way to think about this is if you were holding a desk and carrying it out the door, when you're trying to carry it, it swings around, right? It takes up a lot of space. If you have 2 people, one on each side, that thing doesn't swing at all, does it? It just stays right in the center, and you don't get a lot of movement. Okay? So non-bonding electrons, not restricted. They're going to spread out. They're going to take up more space, like that desk swinging around, right? Okay, so this right here is a lone pair. That's a non-bonding pair of electrons. And so what we can see here is if we were to look at the electronic geometry, that'd be tetrahedral, right? See the camera, little camera stand, the tripod? Okay, and so if you were to look at this just for the molecular geometry, though, it looks like a pyramid, doesn't it? Yeah. So that's trigonal pyramidal. Okay? Triangle base, pyramid. And that's actually what the molecular geometry is. So whenever you're doing the molecular geometry, you want to take those lone pairs and just make them invisible. Okay? They're not there. They're still the same shape for the molecule, right? Just the lone pairs, we don't count those in our what we're calling the shape. Okay, this right here is water, by the way. Anybody know what this is? NH3? Anybody ever used Windex? Or smelled Windex? It's ammonia. Okay. Okay, so this right here is water. And so what you'll see is water has 2 lone pairs, 2 hydrogens. That is 4 electron domains. That gives you a tetrahedral electron geometry. Okay. We ignore the lone pairs. Just look at this shape here. That's bent, isn't it? Yeah. That's the name of it.
How can you know how to draw with the wedge or the wedge structure?
This right here, the wedge dash, is normally you don't actually write water out like this, by the way. That's a weird way to write it. That's what your book did. I took the book bigger. you would just write it flat here.
Yeah.
But the wedge dash, we're copying this over here. And so see how this hydrogen's coming out towards you?
Yeah, I'm saying with like other molecules, so like with other elements,
Mhm.
like for COS, for example, how can I draw that?
How can you draw that?
No, like for COS, for example, like
Mm-hmm.
a couple of different elements in the same compound. A couple of different elements in the same compound.
Yeah,
How
you
can I
just
draw that?
draw them with the O, C, and S.
Mhm.
And then if it's coming out towards you, it's the wedge. It's dash if it's going away from you.
Yeah, how can I divide that?
You look at the three-dimensional structure. So what you'll have to do is you'll have to figure out the three-dimensional structure first. Because these are always a way of representing three-dimensional structure in 2 dimensions. That making some sense? Yeah, if you give me a more concrete problem to talk about, we can get into specifics. Yeah. But without a concrete specifics, that's the most I can give you. Okay, so let's talk about the molecular shape of larger molecules. So right here we have something that's larger. It's not single center, right? You have a center here, you have a center here, and then you'd have another center right there, don't you? Okay. And so all we would do is we would take the same rules that we've been using, and we just use it on each center. Okay? So you go to each center, and you use those rules. So again, that Vesper is that shape of those molecules we're talking about. That's actually that theory that tells you what shape these are going to be. So we go to this carbon right here, and what sort of domains is around that? Well, there are 4 bonds, right? Okay. So we have 4 bonding electron domains around that carbon. 4 domains gives you tetrahedral, doesn't it? And so this one, its molecular and electronic shape, geometry, is tetrahedral. Okay. We go over here, and again, we just have 4 bonding domains, don't we? And so that's tetrahedral again. We go over here, and what we see is we have 4 electron domains. 2 of them are bonding, right? And so this would be electron geometry of tetrahedral, molecular geometry of bent. And so it is bent for the molecular geometry. Is that making sense so far? Yep. See, it's just same rules, same things. We just do it over and over. And then once you have all that, you can assemble it together. So what this would look like is it would zigzag like this. And then that hydrogen would also zag. So you just have like a zigzag pattern. Okay? All right, so let's talk a bit about electronegativity. Anybody ever heard of this term before? Yeah? Yeah, it tends to show up in the sort of better high school science classes. Because it's actually kind of an interesting thing. This electronegativity is kind of funny because the person that came up with this made a joke. So electronegativity is actually a pun. All right, you ready for the pun? So the most electronegative element on the periodic table is a 4.0, like a really good GPA, right? 4.0. If you ace the course, you get 4.0 for your GPA, right? Which is an F. So it's the only time you're going to get a 4.0 for having an F. Come on. You got to appreciate they took an actual theorem and made a pun. Arbitrarily set the maximum number so you'd have an F at 4.0. God, that's just ridiculous. It actually causes a bunch of problems too. Okay, so the electronegativity is actually a measure of how well something pulls the electrons in a bond. So if you have high electronegativity, you can think of it as a tug of war happening when everything's bond, right? High electronegativity is like the super terminator, can pull really well, okay? Low electronegativity is like, 20-pound small child, right? just goes whoosh. All right. And so, again, electronegativity is going to be how well things pull electrons in the bonds. So if you have something with high electronegativity, it's going to pull the bond electrons towards it. There's a big enough difference. That higher electronegativity element is just going to take the electrons from it. That's what happens when you bond a metal to a nonmetal. The nonmetal has higher electronegativity. There's a large difference, and so it just pulls all the electrons away, and it just takes the electron, right? When you have things that are closer in electronegativity, that's when we get things like covalent bonds. So if you have the same electronegativity, you're going to have a fully covalent bond. You share the electrons evenly, right? Now, what would happen if something has a higher electronegativity, but not a huge amount, right? So like you two are wrestling over that pen, right? And you both need the pen real bad, and you're pulling it. Is anybody going to actually get the pen permanently in a short period of time? No, you're going to just end pulling on it. One of you might end up pulling more, right? And it'll be a little closer to you, okay? That's going to be the same thing that happens when you have what's called a polar covalent bond. So it's kind of more ionic, but it's still a covalent bond. You're still sharing. Neither one can pull away the other. But it's not shared evenly, is it? Okay. Okay. And so right here we have the trend for electronegativity. As you go up and to the right on the periodic table, electronegativity is going to get higher. That's why the nonmetals are all up and to the right. Everybody see okay? And then we go less and less as we go down and to the left. And so we get to the metalloids and then the metals. See how the metals are down here on the bottom as well? That's because of this same trend, isn't it? We're seeing the electronegativity trend. Okay. What about group 8A? What in the heck? Does that make me a liar? Mm-hmm.
They don't, because their electron cloud is full, right?
Yes. You got it. Got it. This is a measure of how well something pulls electrons in a bond, right? If you don't bond, you can't measure it, can you? Yeah. And so these just don't bond because their electron clouds are full, exactly, the full shell, right? It's perfect. Okay, so again, when you have this inequality, this is going to occur when you have two different atoms that are involved in a covalent bond. The electrons are going to be shared unequally. The higher electronegativity thing is going to pull the electrons and have those around it more often. Okay? So when you have two identical atoms, they're going to share the electrons exactly evenly. Neither can pull better than the other, right? And so you get a perfectly covalent bond, no polar character whatsoever, no ionic character. Okay? A covalent bond where they're not shared equally is called polar covalent bond because you get one side that's positive, has less electron density around it, one side that's negative, has more electronegativity around it. Notice that is a magnet, isn't it? And so it has polar, as in it has poles, right? Same as the planet. We have poles. What is it called around the poles? The polar circle, the polar, etc., right? Okay. So when the electrons are shared equally, this bond is referred to, if you want to be very specific, a non-polar covalent bond. Technically, you can get away with just saying covalent bond, but people get confused sometimes. Non-polar covalent bond. Doesn't have poles. No charges on it. So this is a case of non-equal sharing right here. This is HCl. And what you see is the electrons spend most of their time around the chloride, right? Less time around the hydrogen. And that's because chlorine here is much more electronegative. Not enough to just take the electrons, but enough to hold on to the electrons more. Here we see hydrogens. They have the exact same electronegativity. Share them equally. That's it. Okay? So this right here is just a covalent bond or a non-polar covalent bond. This is a polar covalent bond. This right here is the terminology that we use to express that polar covalent, the poles of that polar covalent. The one on the bottom is the one you all will probably prefer to use and is honestly the more preferred method overall. Okay? You put a plus where it's positive. See the plus? You then draw an arrow over showing where it's negative. Because the electrons go that way. Is that making sense? Okay. Yeah, it makes a lot of sense, right? Quite nice. Anybody know what that symbol is right there? See, it's a little D looking thing. Sorry, the resolution of this projector is just freaking awful. But
It's just a charge, isn't it?
yeah, it's called a partial charge. Okay. So this small like cursive D looking thing, that's a lowercase delta. Anybody ever seen the capital delta? That's that triangle. Yeah, that's capital delta. Capital delta is used when you have whole number changes, whole unit changes. And then small delta is used when you have partial changes. And so what we're seeing is a partial charge difference, right? Partially negative, partially positive. But not whole electron numbers, which would be ionic bonds, right? Okay. Is that making sense? Okay. It looks a bit like a cursive D. Yeah. Can you guys see that better? Okay, good. Fantastic. Yeah, this is the partially positive here. This is partially negative. Okay. So these bonds are going to be polar, i.e. they have poles. One side's a little bit negative, one side's a little bit positive. Okay. Non-polar, sharing equally, no poles on the ends, no charge overall. Okay. The whole thing has the same sort of charge. Okay. This right here is the electronegativity differences and what you'd expect to see. So when we have 0, we're going to be non-polar covalent, right? And then once we get up to about 0.4, that's when we switch over to the polar covalent bonds. Okay? Under that, it's just not enough difference to really matter, right? This is things down here, just below the 0.4. That would be like a carbon with a hydrogen. Okay? Typically considered nonpolar. It's just not enough difference to really matter, right? Usually not really detectable. This right here is going to be where they're shared on equally. We have the polar covalent bonds. That's going to go from the 0.4 up to just before the 1.8-ish. Okay? That's the sort of differences you're going to see for these polar covalent bonds. We're sharing the electrons, just not evenly. So we're going to have poles. Now, after 1.8 and on, you can actually, 3.3 tends to be the max for most situations you're going to see. You can get some higher numbers, but you got to really set those up. And you're just never going to deal with that. Okay? And so this is where the electrons are actually given away and shared. Like, they're not shared anymore, they're just taken from it, right? This is essentially always going to be, for your cases, metals and nonmetals together. Okay? This is going to be nonmetal, nonmetal, but not the same things. Okay? And then this is mostly going to be nonmetal, nonmetal. Most of the time, same thing. A few cases where it's not the same, but they're not that far on the periodic table. Okay? Like carbon, hydrogen. The truth is that I left out the edge cases in this case. Like, you can actually get metals making covalent bonds on stuff that's way low on the periodic table. Okay? There's some crazy stuff that can happen. Rules are meant to be broken, right? Right. Okay, so this is the electronegativity and the molecular polarity again. So this is the electronegativity difference and where those cutoffs are, in case you forget what I had just talked about. It is possible, of course, to distinguish ionic bonds from covalent bonds. What we do is we look at the types of elements present. If you have a metal and nonmetal, that's going to be a what type of bond? Metal and nonmetal. Ionic, you got it. If it's nonmetal, what are you going to see? Covalent, yeah. You don't typically, you're not going to experience a lot of metal stuff. That's just not within the scope of the class. It has a different type of covalent bond, and I'm not really going to go into it, okay? If you're ever curious, though, come join me in higher level chemistries. We can do some crazy stuff. Okay. You'll see your view of the universe completely shatter and be reformed. All Da, da, da. Okay. So one of the sort of the important things to keep in mind whenever you're thinking about these to distinguish the nonpolar bonds, slightly polar bonds, strongly polar bonds, is fluorine is the most electronegative of all the elements. It's the big bully, okay? It takes and takes and takes from everything else, right? Electronegativities are going to increase as you move towards fluorine on the periodic table, so up and to the right. Okay. The big increases tends to be going from a lower period to a higher period. The smaller increments are usually going from left to right overall. Okay. The further apart two nonmetals are on the periodic table, the greater the polarity of the bond between them. One major exception to that rule is the hydrogen, because hydrogen's put all the way to the left, right? And so hydrogen is really actually just a little bit left of carbon. It's just we have a whole block that doesn't do anything, that exists to be lower, that's like taking up space, right? Okay. So in reality, whenever you look at carbon hydrogen, like shrink that spot in the middle. Just take your periodic table and fold it so you can't see the transition elements. And that's more accurate. Okay? Okay. And so the molecular polarity, molecules can be polar or nonpolar, of course. Polar molecules have uneven distributions of the electrons over the molecule. Nonpolar are going to have essentially evenly distributed electrons over the molecule. The molecules that contain only two atoms will contain a covalent bond. The polarity of the molecules can be determined by the polarity of the bond, right? So all we have to worry about then is the charge distribution across that bond, i.e. one side's positive, one side's negative, right? But what if we have more than two bonds? What if we have more than a single bond that we have to worry about? Like, what would happen if you have more than one magnet? Can you have situations where instead of being positive on one side, positive on negative, you get like negative, negative, positive, positive? Yeah, you can, can't you? Yeah. And so when we start having more than one bond, what we have to do is we have to consider the overall charges, overall pulls. Okay? So for example, CO2 here, this is a linear molecule. Okay? Now, the oxygens here, they would normally be negative, right? And the carbon would normally be positive. And so the bond poles are positive here, negative here. Okay? And then that's true for this one as well. So it's negative on the oxygen, positive on the carbon again, isn't it? Okay. But if we look at our overall molecule, notice what that does to our overall molecule. We're just negative on the outside, aren't we? Yeah. So our overall molecule is actually considered nonpolar. It doesn't have a clear positive-negative pole. It has negative on the outside, positive in the inside, right? So there's not an overall pole. Okay. Water, on the other hand, if we look at water here, what we see is that water, again, has hydrogen is positive and the oxygen is negative, doesn't it? Okay. Now, water is bent, though, isn't it? So what ends up happening is this direction, they cancel out, don't they? This direction, they add together. And so what you get is a negative charge up here on the oxygen, and then a positive charge down here on the hydrogen end, don't you? And so it's actually a little magnet where your negative end is on the oxygen end, the hydrogen end is positive. Okay? And that's the molecular dipole. Right. Everybody okay with that so far? Letting that seep in? Okay. So again, this would be your molecular dipole for water, expressed right here. That's this red arrow. These would be your bond dipoles. Okay. So, again, this right here is your study guide. Did everybody notice I give you these every chapter? And these are your study guides? So, like, if you're curious what you should be studying for the exams, right, I've given you study guides for each chapter, and that's what you'll want to recap and go over, right? And then you'll want to do the homeworks, and those are important problems that I thought you should know, okay? And then you can redo the homeworks or do them for practice, can't you? So if you need to redo those to refresh your memory, And then I also have given you review assignments that are worth 5% extra credit. And those review assignments are over questions that are going to be sort of the stuff you'd see on the exam, right? Okay. And so I can't give you every single question you could possibly see on the exam. The review assignment would be a 5-hour assignment then. I don't think you want to do a 5-hour assignment, do you? No? Okay. Okay. Yeah, that seemed excessive. So I give you a sort of representative, this is what a test that I've previously given would look like. Okay. In fact, it is a previously given test from a while back. Okay?
Is that the review 1 through 3 that you're talking about?
You got it. Yep. What I've done is I've put review 1 through 3, unit 1 is the full name. Did that not come out?
It says review 1 through 3.
Okay. Chapters 1 through 3.
How long will the review take?
The review should take about an hour and a half, hour 15.
Like a normal lesson, but just going over it?
Yeah. Yeah, it's the same sort of time. Exams are 1 hour.
Oh, I was like,
So it's a bit longer than an exam.
oh, okay.
Yeah. Yeah.
And just study everything on that, and it should be good.
So study guides. Those are the material you want to study. Test yourself with the homework assignments and review.
Okay.
That making sense?
Okay, yeah, that's
I don't do exams by questions. So what I do is time. Okay? And then I give you the points for that amount. Yeah. So like the problem with this course is that I could give you later on some of the math questions will take 2 or 3 minutes instead of 1.5 minutes, which is a normal question. Okay? So like those exams later, you'll get more points per question and we'll have less questions. Does that make sense? Yeah. So typically it's somewhere in the like 30-ish.
questions.
Yeah. And it's 50 minutes of questions. That's how I actually do it. All my questions have like hundreds of people that have used them, unless I add a new one.
So they're multiple choice, and we can bring notes, and then do we get scrap paper, or do you want us to just write with our notes?
You can just write on with your notes, or you can use your own scrap paper. I will bring a bit of scrap paper, but probably not enough for everybody. Yeah, yeah, because when I start trying to bring enough paper for 40 people, it gets a little wild, right? Yeah. Okay. Mm-hmm. Could you send me an email to remind me, by the way? Yeah. I will try to put a periodic table into the test itself, and that's my goal. I will probably need a reminder. I just have so many things going on right now.
You said that a normal calculator would work?
Yeah. Oh, yeah.
Isn't it basic?
Yeah. So basic scientific calculator will work fine. Yeah, and you can grab those for at different like grocery stores, Walmart. Most of the like dollar store things typically have them. It depends on the dollar store thing you go to. And the big thing to look for is this test you would be fine with just even a basic calculator, but in general you'll want like a powers and logs. Yeah, and like scientific notation stuff. No problem. No problem. Yeah, having trouble getting the calculator in?
I just haven't like gone shopping yet.
Oh, okay. That's fair. If you have the money, like there's TIs. Okay, so I let you use graphing calculators, and I programmable calculators. I'm fine with that. Some of the math courses don't let you use those. And so what was it, TI 80? I think it's TI 80. That is the like one that most people like when they get it. But they're a little bit more expensive if you don't get them used. If you get them used, they're really cheap. Okay. Anybody have any other questions? Anything? No? Okay, we'll call that a day. So remember, when's the exam again? Tuesday. Fantastic. Okay. We will have a little section where I teach you scientific method and I give you a quiz over, okay? Before the exam starts, remember that will be a grade, so please pay attention and do your best. Okay. have one for that?
It's the one I used on these two.
Most definitely.
Okay.
Yeah. I'm sorry. Did that have a log button? Yeah, you got powers. You have. Where's your? Oh, there it is. There. Yeah.
Yeah, I'm good.
Perfect.
Thank you.
Yeah. Okay.
Can you please show me how to access